Hey guys, so we're going to look at solving a trig question using double angle identities and also doing a proof with double angle identities. So I'm just going to share my screen here, OneNote. Okay, so here's the question. Turn my video off here. Okay, so the question is solving for sine 2x plus cos x equaling 0. And let's solve it over sort of our normal period that we're given. So that the x value will be between 0 and 2 pi. Okay, and you notice here that we have sines and coses, but one of them has a double angle. And one of them has a non-double angle. So basically the period of the cos is 2 pi and the period of the sine function is pi. So this question, we're going to have to manipulate one of the terms to put it in terms of sine or put it in terms of cos. So right now I notice that we have this statement here, and that can be rewritten in terms of its definition, which is 2 sine x cos x. And notice that those two trig terms have the same period as cos x over here. So now we get to this stage. So we could factor a cos out of both terms. And that would leave us with 2 sine x plus 1 is equal to 0. So we solve for the two trig terms. We get cos x is equal to 0 using the 0 product rule. And the sine of x is equal to, when you bring the 1 over, -1, and then divide by 2, -1/2 here. Okay, so the cos graph equaling 0, we could get that by using unit circle or the function cos x. And so we know that it's 0 here and here. And so that would give us an x value of pi over 2 and another x value of that'd be 3 pi over 2. And once again, the unit circle would also give you those answers as well. Now for this question here, we got a negative sign. So that would be in quadrants 3 and 4. And we have a y value of -1, r value of 2. So we have an angle over in the third quadrant. Now this is the 30, 60, 90 triangle. So that reference angle right in here would be, that'd be 30 degrees. And 30 degrees is equivalent to pi over 6 for our reference angle. So theta 1 would be pi plus pi over 6. So pi plus pi over 6. Common denominators are 6's. This gives us 7 pi over 6. And then the other angle would be in quadrant number 4. And this would be 2 pi minus the reference angle of pi over 6. So that's 12 minus 1, which is 11 pi over 6. And that would solve the question between 0 and 2 pi. Now you can see basically from this step all the way down, that's what we've been doing over the past 2 chapters really. So the only really new trick here is this step from here to here. So you're just using an identity to make the question a little bit easier to handle here. So that's using a double angle identity in that case. Here's a proof we can take a look at. And once again, you might want to review your formula sheet here. And you'll see that this proof, there's this 6x here, whereas on the right-hand side, there's this 3x. So it would make sense that we have to turn the 6x's into 3x's or the 3x's into 6x's, so both sides are the same here. So I'm going to start with my identities, and I'm going to use the identity we used above, the double angle identity for sine 2x. So this here would be 2 sine 3x cos 3x. So notice that the identity really is sine 2a is equal to 2 sine a cos a. So we half the angles when we do that, and then we get a 2 in front of the function itself. Okay, and that's all over 1 plus, now cos 6x has 3 different identities we can choose from. And what I'm sort of looking at is trying to get the left side to equal the right side. So what would be really helpful is if I could get rid of this 1 here. So I'm going to pick the identity for cos 2a that allows us to get rid of the 1 here. So there's two cos squared x plus 1, and then there's 1 minus 2 sine squared a. So I'm going to use that. I'm going to use the first one, actually. That was going to be 2 cos squared a minus 1. Okay, so let's write this as 2 cos squared. Now it would be a, but a here is really going to be 3x, and then minus 1 here. Okay, so the ones are going to cancel. They're going to cancel out, and we're going to be left with 2 sine 3x cos 3x all over 2 cos squared 3x. Okay, so you can kind of see where this is going now. So the 2's are going to cancel, and then one of our coses is going to cancel here, and that would leave us with sine 3x over cos 3x, which is just the tangent of 3x. So the proofs are kind of similar to other proofs. We're just trying to combine terms to make it look like the right side, or have left side look like the right side. But what we should notice is that we're using double angle identities here. And I would say probably the cos one is the trickiest of them all, because don't forget cos 2a is also equal to cos squared a minus sine squared a. And it's also equal to 1 subtract 2 sine squared a. So there actually is 3 different terms we can use there, and you kind of have to plan ahead and choose the one that works best. Although technically, if you were to pick technically the wrong one or a different one, you can still get to the right answer. You just have to manipulate a bit further then. Okay, so I'm going to stop the video there, and that'll be the end of the double angle identity part.